Long-term time series of the geomagnetic products. This kind of time series seldom homogeneous because of very many factors which can interrupt the measurements at the particular point of the Earth's surface. And in this presentation, in this study, this work, we study the effects of station relocation in the AA index. First, I remind what station contribute to AA index. AA index has about 140 years time series, and why the concerns about the A index arose, and then we consider more precisely the AA distributions, and then as a conclusion is that AA index is a wonderful example of perfect treatment of geomagnetic data made by you. It is an example for all of us who will examine the long time series in data and geomagnetic indices. The A index of geomagnetic activity is the longest time series, and it was initially calculated by Mayor in 1972, respectively from the year since 1868 onwards. The A index is derived from the two near-antipodal observatories in the both hemispheres, and it represents the activity level in the invariant magnetic latitude about 50 degrees mid-latitude index. For each 3 hours intervals, the K indices are measured in 2 stations and converted back in amplitude, and AA index is an average of the northern and southern values and weighted to account the small difference in latitude in 2 stations. And by averaging of 2 antipodal stations, the annual variation is reduced. This is the 3 AA stations in the northern and southern hemispheres, here and here, and their operation time. Now Heartland operates and Canberra operates, but at the beginning it was Melbourne, which then was turned to Toolangi, and another 3 changes happened during the long time since 1969. The change, the AA stations were relocated in 1920, 26, 57, and 80. The relocation was very close. Despite of that, the magnetic variation was changing, and Mayor suggested the correction factors, which he calculated very precisely. This is the annual means of AA index. For the purpose of space climate, the annual AA index is the most important. And here are the sunspot number, and we can see the upward trend in AA. It's about 12 nanotesla since 1968. And the index generally follows the solar activity, and there is a real signal of solar cycle there. In this plot, the vertical lines represent the years of station relocation. So the first relocation was at the declining phase of solar cycle, and the increase of solar cycle, and during the maximum. The third relocation was just at the maximum, the largest maximum during the last 1.5 years. The geomagnetic index, AA, is very important, and this slide shows the temperature, the global temperature, and the geomagnetic activity represented by AA index. And long-term studies show the same behavior of the geomagnetic activity and the temperature. So the trend in geomagnetic AA index is very important for many aspects of science. However, there is some concerns about the AA index. So different techniques and ultimate measurements of geomagnetic activity put the concerns about the quantitative value of the centennial increase and the long-term consistency of the AA index. And several papers were published where AA index was put under the question. For example, here it is evident some kind of jump in approximately 1957, and here this is a work by Svalgard where he represents the AA index series from the inter-hour index, and also there is some discrepancy, so the long-term trend is different. This is another evidence. This is a multi-year trend and different levels of activity. The AA index less than 10 nanotesla, between 10 and 20, and between 20 and 30. And here we see the downward trend for higher levels of activity, upward trend, and in this diapason of index there is abrupt drop, and when the next level of activity, for next level of activity, there is abrupt. So this figure, looking at this figure, we suspect some kind of inhomogeneity in the AA index, especially evident in 1957. So the question arose, are the 3 hours AA index time series inhomogeneous? Does the index depict an excessively large centennial increase? And does the AA contain any discontinuous due to possible station intercalibration problems when AA station was changing in 2026, 57, and so? As a result, Yaga Division 5 business meeting in Perugia posed the question, should an official Yaga sanctioned correction be made? And if so, it will be quite difficult to make sure that any chosen correction methods are indeed valid and well-founded. And this motivates the study which was performed. This plot shows the annual frequency distribution of each AA values in each year, but different AA values from 2 nanotesla and up to its maximum. This is an indicator of long-term stability of the AA index beginning from the beginning of observation and onwards. Here is the diapason of AA between these values. This is the less level. This is the next level of activity, and what we can see, each station relocation year coincides with a jump in AA index. So visually, it is evident one upward jump, downward jump, and 2 upward jumps also. So thus, both the AA changes during these jumps. This is our next level of activity. It is even more evident jumps upward, downward. The largest jump in 57, and again this upward jump in 80. This is the highest level of activity, and frequency is much less. So we limited our consideration by 200 nanometers. And here, this slide represents the effect of jumps on 3 adjusted AA values, the time evolution of annual occurrence of AA with 30, 31, 33, the most frequent AA values. And here it is clear how this value is changing in the year of changes of station. First, we have only stopping, and then the next station, the next change of the station, this value of AA absolutely disappeared and replaced by the next AA value, and then appear again, and then disappear and replace it. And finally, it is replaced by more higher value of AA. So it is seen that annual occurrence of the dominant AA value closely follows the centennial increase in the solar cycle variation, similar to the full annual AA index. And distribution of AA values is a natural consequence of the station-specific coefficients that were derived from station intercalibration by Mayo. And here we consider more precisely the jump in the first jump in 1990-2020. This is a contribution of in nanotesla of different categories of early AA index. This is the level. The AA was divided into different levels of activity. Here the highest level of activity, the lowest level of activity, and the highest level of activity. And here we can see how the different levels changed when the station was changed. The third category, AA between 40 and 70, is the largest contribution to the annual AA index in 99, while the second category has the largest share in the next year. And except the first category, the smallest AA, the other categories that give a negative contribution over the jump. So, despite here in the distribution, the visual effect of the upward jump, the actual AA index go down. So, the upward jump, but the index go down according to solar cycle. Solar cycle also go down. And here, in this plot, we can see the occurrence of 3 hours AA values within each category of activity, and also we can see the positive value, the larger value for the 20 year, only for lowest AA level. And here, the evaluation of the effect of jumps and the difference between consecutive years for each AA value, for each AA value from 2 to its maximum during the relocation in the corresponding years. AA is the contribution of all possible values to each yearly average AA, and this is year, and this is A value, and we consider this the magnitude of these parameters and look at how it changed contribution over each of 4 discontinuous. Also the difference between the successive years. And we can see that only the immediately disturbed AA value between 20 and 70 nanotesla are affected, mostly affected by the recalibration, and the degree of spread corresponds to the intercalibration coefficient. Larger the coefficient, larger the intercalibration, and each jump, positive jump of AA index is compensated by the negative jump for 2 last relocation, but when the A index keeps the same value, but for the first two relocations, there is prevalence of negative variation, negative values, which correspond to upward change in AA index in this year, and prevalence of positive values, which correspond to upward change in AA index in this year. Okay? So we find no obvious evidence that excessively large rise of AA index during the 20th centuries would be due to erroneously estimated station coefficients. Rather, the station intercalibration seems to have been conducted reasonably correctly, reproducing the solar cycle variation, but not leading to artificial jumps. So the changes in AA index over the 4 jumps are in agreement, both in sign and magnitude, with the solar cycle variation. The possibility of an erroneous calibration in 1997 is responsible for a significant part of the large increase of the AA index seems unlikely. Such possibility has been mentioned in literature previously, but the reason is not the mistake of my youth. My youth is perfect. So there is no jump of 300 Tesla in 1957. So, and the fact that AA index depicts largest and shale increase than similar global and local mid-latitude indexes derived from the interannual or inter-daily variation is due to some other unknown factor. Maybe it concerns the treatment of the old magnetograms, maybe the change of sensitivity of the magnetometers. It is some kind of suspicion that in Ebinger, the magnetometers changed the sensitivity 2 times. The sensitivity of Ebinger magnetometers was 2 times smaller than other magnetometers, and this can affect the AA index. This is an illustration how careful we should be in the recording of the magnetic variation, and how careful we should be in any correction and any creation of products, not the raw data.